Okay, good morning. So we continue the lesson of more on polynomial equations as we started last time. So if you remember, let me just start with the example today and then try to refresh your memory about that. So solve the following equation. In the set of complex numbers. So x to the 3 plus 3x squared plus 3x plus 2 equals to 0. Okay, so if you remember what I said before, if you want to solve a polynomial equation whose degree is more than 2, then in order to be able to solve that, you have to be able to factorize your polynomial. But factorizing a polynomial in usual is not that easy. If you remember, there were type of problems that consisted two parts. The first part gives you a root of this equation, and then using that root, you're supposed to do the long division and find the other roots yourself. The long division will help you to factorize the polynomial. But there is some question is that if they just give me a polynomial equation of higher degree and then don't give me any extra piece of information, can I still do something with that? Yeah, I would say yes. So that is the content of a theorem that I want to mention here. If you have a polynomial equation whose coefficients are all integers, so let me just write this theorem. Of course, this theorem is not part of the solution. I am using this example as an excuse to talk about these things, okay? And then after that, we use these things that I mentioned here to solve this problem. So the theorem is this. Let p of x be a polynomial with integer I emphasize on it, integer coefficients. If an integer, again, so let me write the polynomial because we need to write the polynomial here. So if an integer, so let me write like this. If an integer x naught is a root of p of x, then x naught is a divisor of the constant term of p of x. Okay, so what does it mean? It means that if you have a polynomial, forget about the zero part. If you have this polynomial whose coefficients are all real, 1, 3, or minus 3, doesn't matter. Coefficients should be integers. If there is if an integer x naught is supposed to be a root of this equation, then this number should be a divisor of the constant term. But be careful, it doesn't mean that every divisor of the constant term is a root. But if there is an integer root for this, you know where to look for them. You just go there and find the constant term, write all the divisors of 2 here, plus or minus 2, plus or minus 1. These are the only 4 ones, yes? And if this equation is supposed to have an integer root, this root is among these 4 numbers. And then, of course, you can start checking them one by one. And if you are lucky, and usually in the exam problems, if they haven't provided you an extra piece of information, this is usually indeed the case, that you will find an integer root. And then when you find an integer root, then you can use the long division method to factorize it. So that's the idea. So let p of x be a polynomial with integer coefficients if, there is no guarantee of course, if an integer x node is a root of p of x, then x node is a divisor of the constant term of p of x. Okay, first of all, let us understand why this is true. Okay, so why this is true. So I would say that proof. Let me write everything in blue. So let p of x, let us write it. It's a polynomial. So let me start with an. Yes, an x to the power of n plus a sub n minus 1 x to the power of n minus 1, and then up to a1 x, and then plus a node. I have a polynomial. I don't know what the degree of that polynomial is. I am just assuming that this is of nth degree, whatever n is. And then I have written a generic polynomial of degree n. But I am assuming that all these number a's that you see here are integers, yes? Where ai's are all integers, yes? Okay, now the theorem assumes that x node, which is an integer, is a root. Okay, so x node belongs to z according to the problem, and p of x node is equal to 0. Why? Because you're assuming that x node is a root, so it means that it satisfies this equation. If I replace x with x node, I will get 0. That's the meaning of being a root. Okay, but what this means, p of x node equals to 0, means if I replace x in my polynomial with x node, I will get 0. So this means that an x node to power n plus an minus 1 x to power n minus 1, the x node to power n minus 1, up to a1 x node plus a node is equal to 0. Yes? That's the mean. But what can I do? All these terms from here to here contain at least one x node. So I can take this up to here and factor an x node out, yes? So what I can do, I can write it in this form. X node multiplied by an x node to power n minus 1 plus an minus 1 x to the x node to power n minus 2, and it continues until this term, which becomes a1, but of course I have plus a node, and I move it to the other side, it becomes minus a node. Yes? But now let me ask you, what type of number do you expect to appear here? Yes? Let us look. X node was given to be an integer, and then ai's, which are the coefficients, are all assumed to be integers as well. So if you put those numbers here, you have an integer, you raise it to a positive power because polynomials are positive, include only positive powers. So this is an integer, to some positive power, it becomes an integer, multiplied by another integer, it becomes an integer. So every term that appears in this big pair of brackets is an integer, so when I add them, it's also an integer. Yes? So this means that this definitely belongs to Z. Okay, so I can give it a name. So the people who had math 4, so that's actually, you can give it a name, yes. So you can say that x node multiplied by some number, so let me call it q. I give this big thing the name q equals to minus a node. But what does it mean? So if you can just multiply everything by minus sign, so you get x node. I multiply the minus sign for the left up to the q, and it becomes a node. Okay? But this is important because this q is in Z. This is also in Z. This is an integer. So now what do you have? You have x node multiplied by an integer is equal to a node. So it means that a node is divisible by x node. Or you can say that a x node is a divisor of a node. Yes? So this means that x node is a divisor of a node. And that is what I wanted to prove, yes? I wanted to show that if x node is a root of p of x, then x node is a divisor of the constant term of the polynomial p of x. The constant term is of course here, and I was able to show, yes? But be careful, the converse of so this theorem doesn't guarantee that if you go and find the divisors of this constant term, all of them are roots of this equation. No. It tells you that if this equation is supposed to have an integer root, you know where to look for them, to find them. You go and find all the divisors of this number, and then you look for them inside that. So for example, in this case, if I want to see that is there any integer root for this polynomial with integer coefficients, the first thing that I do, I will go and find the constant term, and I will write all the divisors. So what are the divisors of 2? The numbers that 2 are divisible by. So it's 1, 2, minus 1, minus 2. These are the only numbers. And if this equation is supposed to have an integer root, I know where to look for them. It is among these 4. It means that if I check these 4 and none of them is a root, it means that I have to give up this idea that this equation has an integer root. It might have different roots, yes. And then by my experience, this you don't need to be worried. So if you are given a polynomial of the degree of higher than 2 and you're supposed to solve it without any guidance in the first part of the problem, then it's a really good thing to go and look for the divisors of the constant term and then try to check them. Okay? So for example, here I even don't need to check 1 and 2. There is no hope for them, yes? Because all these numbers are positive. If I put positive numbers instead of x, this is clear that I will not get 0, okay? So I really don't even bother to check these things. This cannot happen, this cannot happen. The only problem is that probably with minus 1 or minus 2. If minus 1 or minus 2 is not a root, we have to give up this method. We have to find a way to factorize it, yes? Okay, so let us check. For minus 1, I put minus 1 there. Then it becomes minus 1 to power 3 plus 3 minus 1 to power 2 plus 3 times minus 1 and then plus 2. And I ask myself, is it 0 or not? Is it? So this is minus 1. This is plus 3. Minus 3 plus 2. No. It's not correct. Yes? So this means that minus 1 is also not a root. Okay, so let us go and see minus 2. What happens for minus 2? If I put minus 2 here, it becomes minus 2 to power 3 plus 3 minus 2 to power 2 plus 3 times minus 2 and then plus 2. So let me see if this is correct. This is true that this is 0. So then what happens here is minus 8. This is 4, 12 minus 6 plus 2. Is it correct? Yes. So this is 0. So this means that yes, at least we realize that this is one root. I'm saying that there is no guarantee. It might happen that this is not indeed the case. Then we have to give up this idea that there is an integer root. At least we can say something. There are no integer roots for this one equation. Okay, but now it turns so do you remember? From now on, do you remember in the previous problems I gave you two parts, the first part, the second part. The first part was a guide for the second part. So I was telling you in the first part, okay, check that minus 2 is a root, and then I ask you to solve the equation. But this one, you did it yourself. So you found that minus 2 is a root. So what does this mean? So you have to go to the long division method, as we learned before. So we'll learn this. So since P of minus 2 is 0, we just checked that. I put minus 2, I got 0. P of x is divisible by which polynomials? You see, you know that P of x should factorize in a way so that one of the roots of this polynomial at least is minus 2. So it means that you should expect a factor appears in its factorization. What that factor is, one of the factors you are sure about. What is that factor? You know that P at minus 2 is supposed to be 0. So it means that if you factorize P of x, I don't know how many terms will be involved, but at least you know one of them exactly.
X plus 2.
X plus 2. Yeah, so because it is clear that if I put this equal to 0, one root should be minus 2. So it means that one of the factors should be x plus 2, so that when you put it equal to 0, you get x equals minus 2. Okay? So this is why we actually is divisible by x plus 2. Okay? And now that we know my polynomial is divisible by x plus 2, I can use the long division method to factorize it. How? I write my polynomial x to the 3 plus 3x squared plus 3x plus 2, and then I write, I don't know, this way of writing, so something like this, and then you put that expression here, x plus 2, and then do the long division. What was long division, if you remember? You just take the first term of here. First of all, you have to write them in a descending order of powers of x, here and there. Okay, this is important, okay? After you have done that, you take the first term here and divide it by the first term there. We ignore the rest of it, forget about them. X to the 3 divided by x, the answer is of course x to the power of 2. You put x to power 2 here. And then you take this one and multiply it by the whole expression, not just the first term, and change the sign of each term and write it here below this. So x2 times x is x cubed. I write it here, but I have to change the sign. And then I multiply x squared by 2, it becomes positive 2x squared, but I told you that you change the sign. And when you did that, so you start adding this polynomial to your original polynomial with similar terms, of course. So this one and that one are similar and opposite, so they are gone. And minus 2x squared is similar to 3x squared. If you add them, 3 of them minus 2 of them just becomes 1 of them. And then you bring all the terms that are not touched down, yes, but in order. So I mean that I don't bring 2 first and 3x. I have to bring 3x first and 2 second. Okay, and then when you do this, you repeat the process. Because you have already guaranteed that this is divisible by x plus 2. When you do this calculation, you end up with 0 at some point. If you do not end up at 0, it means that you have done some mistake in your division. Okay? So let us just repeat the process. Again, I take this first term, and I take the first term here as well, and I divide them. So it becomes x squared divided by x, which is positive x. I put positive x here. And then I multiply this by the whole expression and change the signs and put them here. So x times x is x squared, but I change the sign. X times positive 2 is positive 2x, I change the sign. And then I do this once more. So if I now add them, this is and that one are gone. Minus 2x plus 3x is just x. And then I bring 2 down, so it becomes 2. It's not finished yet because I haven't got 0 yet, but this is clear that this is the last part. I will take the first term again and divide it by the first term. It is positive 1, so I put positive 1 here. And then multiply 1 here and write it there with opposite sign. So it becomes 1 times x is x, I write minus x. 1 times 2 is 2, I write minus 2. And you see that when I add them, it's nothing left. And then I told you that the name of this guy is the dividend. Dividend. This is called the quotient, what you get. And this is called divisor. And this is called remainder. Of course, in this case, remainder is always 0. And then how this will help me to solve the problem, whenever you've done this and you got 0 as your remainder, you can write p of x is equal to your divisor multiplied by your quotient. Of course, plus the remainder, but the remainder here is 0, so you don't need to add anything. This is the factorized form of your polynomial. So this is the very long process. What is the typical problem that you might get if you don't have any guidance there? So just go and find the factors of the constant term and try to check them one by one, or the more reasonable ones. And as soon as you get one, you do the long division process, and then you get the factorized form of your polynomial. But the rest of it is easy, because we are supposed to solve, here it's written solve the following equation in the set of complex numbers. Now that I have my polynomial in its factorized form, it is not hard to solve it, yes? So what I do, I would say that p of x equals to 0 means this product is 0, but this is the product of two numbers. This product is supposed to be 0, so this means that either this one is 0, which is of course of no surprise for us because we already know this answer, or the other one, x squared plus x plus 1 is equal to 0. So this, of course, this gives you x equals to minus 2, which is acceptable in this case because every real number is automatically also a complex number, so you shouldn't exclude that, that's also acceptable. But then what happens here is x squared plus x plus 1 equals to 0. We have to solve that. Okay, so then you use the ABC formula. It's minus b, which is minus 1 plus or minus the square root of b squared, minus 4 times a times c, which is minus 4, divided by 2. Now you see that this is a complex number. This becomes x equals to minus 1 plus or minus the square root of negative 3. But the square root of negative 3 is square root of positive 3 multiplied by the complex number I divided by 2. So if I want to write it more properly, so the answer to this problem are 3 roots. Yeah? So one of them is negative 2, the other one is minus a half plus the square root of 3 over 2i. The other one is minus a half minus the square root of 3 over 2i. Yes? Any questions? So this is something you need to know here. Okay, another part of the lesson that I want to start here is actually the simplest possible polynomial equations. Not these harder ones, but it turns out to be something totally new for you probably. For example, if I ask you to solve z to power, let me just use the variable z instead of x because we're working in complex numbers. It is better to have them named with z rather than x. So if I ask you to solve this equation when you are doing Math 1C, I think you can immediately answer that, and there is only one root to this equation, and that is z equals to 1. So 1 is a root to this equation, because if I replace z with 1, I raise it to power 3, it becomes 1. So definitely z equals to 1 is an answer. But now, if I go to the set of complex numbers, I might ask you, are there other solutions to this equation when I am working in the set of complex numbers? Okay, so we want to solve this simple polynomial equations of this type. Z to power n equals to a complex number, so w. So z and w are supposed to be complex numbers. These are also polynomial equations because when I move this to the left-hand side, it becomes a polynomial of degree n whose constant term is w. But this is important, so we just pay attention to this separately. Okay, we want to understand how we can solve these problems. Okay, can you guess any other number whose third power is 1? Of course, in the set of real numbers, there is no hope for looking for those numbers. Z equals to 1 is the only one. So they are if there is something more to it, that should be a complex number. Okay? Okay. By the way, let me test your understanding. If I ask you what is z squared equals to 1, so what are the answers here? What are the answers to z squared equals to 1? What are they? Plus and minus 1, and we shouldn't expect more because this is a second degree polynomial, and we learned that the second degree polynomial can have at most 2 roots, and when you already say plus and minus 2, it means that this is done. But let me ask you this one, z squared equals to minus 1. What are the roots here? In the real numbers, we don't have any roots because we do not have a real number to power 2 to become a negative number, yes? But in the set of complex numbers, what are the roots? You need a number whose second power is minus 1. So what's the famous number? It's I, yes? I squared becomes minus 1, but there is more than that. One of them is I squared, the one of them is I, the other one is negative I. So it's simple. So if a z equals to plus or minus I will definitely satisfy this equation, yes? Because when you raise this to power 2, this minus or plus sign are gone, then you get I squared, but I squared is always minus 1. And because this is a second degree polynomial and we were able to find 2 of them, so it means that this is the solution. But of course, if I increase the power, then we want to solve it systematically, not by guess. Not by guessing. Okay, so how can I solve the problem systematically? So this is one of those cases, again, the polar form is good to understand. Okay, so what we say is that I am looking for a complex number whose third power is 1. I would say that let that complex number that I am looking for be of this form, r cosine theta plus I sine theta. This is a reasonable assumption because if you have a complex number, every complex number has also a polar form. So I am assuming that there is a root for this. If there is a root for that, I can write it in this form where what is r? R is the absolute value of this number, and then theta is the argument of that number. Yes? Okay, so then what happens here? Then this means that I put this into that equation. But we already know what to do with this polar form to high powers. We don't have any trouble, yes? When I want to raise this to power 3, I raise this one to power 3. But even though I am supposed to raise this to power 3, but we have the Demoir's formula, which is simple. Yes, I don't need to really expand that. What I need to do, I take that power of 3 and multiply it here by the argument. So I will get cosine 3 theta plus I sine 3 theta. Yes? And then on the right hand side, I am supposed to have 1. Yes? But what is the question? I am looking for z, don't forget. My goal is to find z. But in order to find z, I need to know r, I need to know theta. Because if I know r and I know theta, I put them here, do some calculations, and I get my z. That's my answer, yes? Okay, but r is easy to find. Yes, why is that? Because you remember what r was? R was the real number, which was the absolute value of your complex number. So what I'm saying is that if this complex number is supposed to be 1, 1 also can be interpreted as a complex number. So I have a complex number on the left, I have a complex number on the right, they are supposed to be equal. So this means the absolute value of the number on the left should also match with the absolute value of the number on the right. So this immediately gives me r, okay? So I just want you to see that what happens. This means that r to the power of 3 is equal. What is r to the power of 3? R to the power of 3 is the absolute value of this combination, is equal to the absolute value of 1. But absolute value of 1, of course, is equal to 1. And then I am asking you, r to power 3 is 1. Then I say that r is what? R is 1. Yes? By the way, let me ask you this. I want to make sure that you understand what is going on. You see, r to the power of 3 is equal to 1. I am telling you r is equal to 1. But when I started the problem, it was z to power 3 equals to 1. I am just giving all this lesson to you that the answer is not 1. Might be we have more. So it means that I am changing the name from z to r, and I am just solving the problem like this. How do you answer this question? Do you understand what I mean? Because this equation and this r to the power of 3 equals to 1 more or less are the same thing, except for the name of the variable. Yes?
Didn't you say r is supposed to be
real? That's the point. Here I am looking for complex numbers as well, but here r is the absolute value of the complex number. The absolute value of any complex number at the end is a real number. So here I have an extra piece of information. Not only r to the 3 is supposed to be 1, but also r is a real number. So in that case, that's not a circular argument, I want you to understand. Here I really safely conclude that r is 1. Okay? Now that r is 1, I put this back into this equation, yes? So therefore, what happens, instead of r, I put 1, so it's gone. So it becomes cosine 3 theta plus I sine 3 theta, yes? Is equal to 1. But I have a complex number on the left. The real part is cosine 3 theta, and the imaginary part is sine 3 theta. But the imaginary number on the right, the real part is 1, the imaginary part is 0. So if a complex number is equal to another complex number, it means that the real parts should match. And, this curly brackets here means and, sine 3 theta, which is the imaginary part, should match with the imaginary part, which is 0. Yes? And then look, what is this theta? This is the unit circle. Cosine is the x-coordinate, if you remember. Sine is the y-coordinate. So the x-coordinate of a point should be 1, its y-coordinate should be 0, so this means that this point is here. Yes? So if I ask you what 3 theta is, you can answer all of it to me, yes? There are infinitely many thetas, of course. So what are 3 thetas? So you see that the end of this 3 theta should end up somewhere here. But which angles end up here? One angle is 0. The other angle is 2 pi. The other angle is 4 pi. The other angle is 6 pi. So every even multiple of pi is there. So this means that from that one, I conclude that theta, 3 theta, which is my angle, is an even multiple of pi. What is n? N so far is an integer. Okay? Okay. But this is something important. You might assume that I have infinitely many answers now because I got r equals to 1. Okay, that is a fixed number. But how many answers did I get for theta? Because theta is this number divided by 3. And I am telling you that, of course, reasonably correct, that n is an integer. So I have infinitely many choices for n, which gives rise to infinitely many choices for theta. This is already a little bit of contradiction. Why? Because I have a 3rd degree equation. I expect exactly 3 roots. But apparently I have infinitely many degrees of freedom for theta. How do you answer this question now? Yes?
That it doesn't matter for the sine and cosine are the same. So
After a while. Yes, exactly. Exactly. So it means that because sine and cosine are periodic functions, what matters for me, of course, I was a little bit careless when I told you that I want to find theta. That was not completely wrong. But what matters is the combination of cosine and sine. It might happen that I have very different angles, but the sine and cosines are still the same. If they are the same, they will not give rise to different answers for me. They will give rise to the same answer. And I don't want to repeat them, yeah? So I have to categorize them, how many distinct solutions I will get. Okay, so how many distinct solutions I will get here? Can you tell me? For example, let us first work with the positive numbers. If I put n equal to 0, so by the way, let me just write it here in front of you. So theta is 2/3 n pi, yes? But if I put 0 for 3 theta, let me work with 3 theta for a while. So 3 theta becomes 0. If I put n equals to 1, 3 theta becomes 2 pi. If I put n equals to 2, 3 theta becomes what? 4 pi. Yes? Okay. Are they different, by the way, or should we work there? So let me see. If I put 0 there, what I get... okay. Oh, sorry. I have to work with theta. Because 3 theta is not important. What matters at the end is this theta I'm looking for. Okay, so I put 0 here, n equals to 0. Then what I get, theta is 0. Okay? If I put n equals to 1, this means that theta is 2 pi, 2 over 3 pi, if I put 1 there. And if I put 2, then this means that theta is 4 over 3 pi. Yes. Okay, if theta is 0, what is the answer to z? Because you remember, I am looking for z. R is already 1. I don't have any trouble with R. So R is 1. If theta is 0, then z is equal to 1, because that is R, cosine 0 plus I sine 0. Yes? What do I get? I get cosine of 0 is 1, sine of 0 is 0, so the answer becomes 0. This is the answer that you could predict immediately, yes? Z to power 3 is 1. What is one of the answers? Definitely everyone knows that z is 1. But let me just calculate this one as well, okay? So this means that z is equal to r, which is 1, and then I have cosine of this angle, 2 pi over 3 plus I sine 2 pi over 3. 2 pi over 3 is 120. 120 is supplement to 60 degrees. So if you do those calculations, you immediately get the numbers. Cosine of 120 degrees is negative of cosine of 60 degrees. So it is minus a half. but this becomes a square root of 3 over 2. I have it in my memory, okay? But of course, you don't have these things probably in the table, so you have to do some analysis. So 120 degrees and 60 degrees are supplementary angles. And we have already studied how they are related, okay? So this becomes minus a half, and then this becomes plus a square root of 3 over 2i. And this is one of those answers we were not able to guess. So this is another root. If you don't believe, you have to be patient. Raise this one to power 3, then you will get 1. Okay. And then another answer is this one. Z is equal to, again, R is 1, but this time I have to put this angle, and then we will see what happens for the rest of the angles. Okay, so this becomes this plus I sine 4 pi over 3. But what is 4 pi over 3? 4 pi over 3 is 240, and 240 is 180 plus 60, and if you do those calculations, you will get the numbers here. So cosine of 4 pi over 3 is pi plus pi over 3, so it is also, it becomes minus a half, but this time this also becomes minus a square root of 3 over 2i. So far I got one answer, the second one, and the third one. Okay, and probably you can guess based on your previous knowledge, because that's a third degree polynomial, this would be the end of the story. But why I get more solutions, I just want you to understand you don't need to go further than that. Okay, because if you continue, it doesn't matter of course, but you will start repeating these processes. Okay, because that's sine and cosine functions are periodic, yes? If I put 3, what happens? If I put 3 here, theta, of course, is different. Theta is not in my list. It's a new theta. But it doesn't give rise to a new z. That is important. And what matters for me is z, not theta. Yes? So you see, when I put 3, I get a theta which is not already in my list. But it doesn't matter, because when I put this to find z, what I get is cosine 2 pi plus I sine 2 pi. But cosine 2 pi is 1, sine 2 pi is 0, I will get 1 back. Yes? And if you start continuing, you will get this 1 by 1 again. And if you just put negative numbers, because when I say that n belongs to z, I also need to consider negative numbers. But again, if you put negative numbers, you get distinct thetas. But this will not give rise to distinct z's, except these 3 numbers. Okay? So this means that we really don't need to continue, and that's the end of the story. Okay, and as a rule of thumb, I tell you that if you have z to some power equals to 1, the numbers that you choose, if you have z to power k, the numbers that you choose are 0, 1, 2, but up to k minus 1. So this, you can remember that, okay? So if you want to produce distinct values for z, the number n that you choose starts from 0 but goes up to 1 unit less than the power in the equation. Yes? Is that clear? So this, we have 3 roots. And by the way, that's also good to know. What are these roots on the unit circle? This is also always the case. So if you draw a circle whose radius is absolute value of the roots. If I ask you what are the absolute values, you even don't need to calculate. The absolute values are all equal to 1. So it means that in this case, if I draw a circle centered at the origin with radius 1, because the absolute value of all these numbers are equal to 1, it means that all of them lie on this circle, because the distance from those points to the origin are supposed to be equal to 1, because the absolute values are 1. Okay, but where are they? So one of them is z equals to 1 is here. Okay, that's also good to understand its geometry. Okay, so the other one, this minus a half and a square root of 3 over 2, so is 120 degrees, yes? So we had this 120 degrees. So it means that the argument is 120 degrees. So another point is here. This one, do you remember? It was 240 degrees. So it means that it is somewhere here, yes? And then the point is that if you connect these points, I haven't done it very precisely, but then it becomes an equilateral triangle. Okay, so that's always the case. You will always get a regular polygon. Here I got a regular trigon, which is a triangle. Why? Because the power that I started with was 3. If I started with the 4th power, I get a regular fourgon, which is a square. I don't know, if I start with z to power 5 equal to something, I get a regular pentagon, yes? And then something like that. So the geometry is also good to know. So what you can do geometrically, if the algebra is complicated, you want to understand that, you find one of the roots and then try to start rotating that root. Of course, that's not also easy, but understanding it, you see the first root that I found is this one. Okay, I have 360 degrees, the full circle, and I have 3 roots, so I divide it by 3, it becomes 120 degrees. So this means that if I can locate one root, then I start rotating that root 100 degrees, okay, and I will get the other roots. So I started from here, I rotated 120 degrees, I get this point, which is this number. I start rotating this one 120 degrees more, I will get this point. And of course, if I want to rotate it again, I will get the same point back. So that is also good to know from geometrical point of view. So algebraically is this, but it is also good to understand it geometrically. Yes? Is that clear? Okay, so let me give you another one, which that you start with a complex number also on the right, okay? And then probably more or less we are done. Okay. So, for example, you want to solve this. Let us write z to power. So let me write 2 z to power 4 is equal to okay, let me write and see what happens. Okay, so we write this. Okay, so we want to solve this equation. So we are looking for all those complex numbers so that when I raise them to power 4 multiplied by 2, it becomes this number. But you know how many of them are there because that's a 4th degree polynomial and I'm working in complex numbers. Including multiplicities, I will get 4. But of course, in these kinds of problems, you always get exactly 4. Okay, so how we should do that? The first thing that I will do before starting that process, I will divide everything by 2, okay? So what I do is this. So I would say that z to power 4 is 1 over 2 plus 1 over 2i, okay? Okay, then I would say what? I would say that let z that I am looking for is this complex number. So r is not known, theta is not known. Okay, and then what I do, I put it back into the equation. Okay, so let me just write all the details. So this becomes r cosine theta plus I sine theta. When I put this expression to here and raise it to power 4, I get a power 4 here, I get a power 4 here. And on the right hand side, I will have 1 over 2 plus 1 over 2i. The hard part is this one, but the Demoir's formula makes it easy, yes, because I put 4 here. This becomes r to the 4 cosine 4 theta plus I sine 4 theta is equal to 1/2 plus 1/2 I. Okay, when you reach to this step, the first thing that you need to do is to compare the absolute values. If I ask you what is the absolute value of the number on the left, it is easy, r to the 4. Yes? And if I ask you what is the absolute value of this, you have to do some calculations, a very small one. So if I want to calculate the absolute value of this number, I would write square root of the first one squared plus the second one squared, which is 1 over 2. And this is 1 over a square root of 2. Okay, so because this number is supposed to be equal to this number, so it means its absolute value should match with the absolute value here. So this means that r to the 4, which is the absolute value of the left-hand side, should be equal to the absolute value of the right-hand side, which is 1 over square root of 2. And I am looking for r. R, now be careful. This is not more or less the same equation. R is a positive real number because it's absolute value. So this means that r is real, r is non-negative. So this means that there is only one r found here, not plus or minus. Because in general you put plus or minus, but because r is non-negative, there is no need to put plus or minus. So this becomes, oops, I'm putting plus minus myself. So this becomes 1 over the 4th root of the square root of 2. Yes, so that is r. But instead of writing this 4th root of the 2nd root, I can just simply write the 8th root, yes. So this becomes 1 over, so this means that my r is 1 over the 8th root of 2. Good. And then, after I found r, I have to find theta. But this one, I take r to the 4 and replace it by what I know. So instead of r to the 4, I put that number in. Okay, multiplied by that expression. This is supposed to be equal to that number. But for simplicity, let me multiply everything by square root of 2. Then I will get this result, cosine 4 theta plus I sine 4 theta. But when I multiply this by that number, this one becomes a square root of 2 over 2 plus a square root of 2 over 2i. Yes? So I get this. But then look, I have a complex number on the left, I have a complex number on the right, they are supposed to be equal. This can only happen if the real and imaginary parts match, yes, correspondingly. So it means that cosine 4 theta is 1 square root of 2 over 2, sine 4 theta should also be square root of 2 over 2. But then I ask you where this 4 theta is. If you're a little bit familiar with these numbers, you can also go. Of course, in principle, if these numbers are not familiar, the only thing we can do is to use the calculator to find theta. But in these numbers, these are familiar for us. So I don't know if it's also familiar to you. No, this is square root of 2 over 2, square root of 2 over 2 is 45 degrees. Yeah, so this means that 4 theta is 45 degrees. You express it in radians. But of course, you can go around and come back again. So you remember it is just 2 n pi plus this one. be careful, I am not solving this and solving this separately. I'm looking for an angle for theta so that sine and cosine of it are simultaneously equal to that number. So there's only one angle for that, and that's 45 degrees. But then, of course, it is clear that when I start from 45 degrees, I go one full round and come back again, I will get the same results, yes? And then I told you that you are looking for what? You are looking for theta, so you divide everything by 4, so this becomes n pi over 2 plus pi over 16. So this is the theta, and of course, I told you what is the rule of thumb. Of course, in principle, n should be every integer number, but I told you that. Look at this power. The power is 4, so you start from 0, 1, 2, up to that power 1 unit less, up to 3. Yes. So these are the numbers that I get for n. Okay, so then you have to replace n and get your thetas, yes? So if n is 0, theta, I put 0 instead of n, so it becomes pi over 16. If n is 1, theta is, instead of n I put 1, it becomes pi over 2 plus pi over 16. But if I do the common denominator, so it becomes 9 pi over 16. Am I right? Yes. And then if n is 2, theta becomes pi plus pi over 16, which is 17 pi over 16. And finally, when n is equal to 3, theta is 3 pi over 2 plus pi over 16. And if I multiply this by 8, it becomes 25 pi over 16. Of course, if I choose other numbers for n, definitely I will get different results for theta, but theta doesn't matter, z matters. But what is z, by the way? So don't get confused. You want to find z. So what is z? Z is r times this combination. But r is this number. So this means that z is 1 over the 8th root of 2, and then multiplied by cosine of theta, which definitely I don't think no one could guess. Yes, this is one of the roots of this equation. So if you are patient, raise it to power 4, multiply it by 2, you should be able to get this number back. So that's one of the roots. And then, of course, you repeat that process for other variables. So r is always the same number, but the angles are different, yes? By the way, you might say that I don't like this form. This is a polar form. I want the Cartesian form. So then, of course, you have to put these numbers in your calculator and get an approximation for the Cartesian form of your complex number. But that's not needed. So z is 1 over the 8th root of 2. Then you have cosine 17 pi over 16 plus I sine 17 pi over 16. And finally, when this is the case, z is 1 over the 8th root of 2 cosine 25 pi over 16, and then plus I sine 25 pi over 16. Yes, these are the solutions for this very simple equation. So the solution seems horrible, but it's not that bad, yes. But let me also tell you what is the meaning of geometrical idea. So you realize that if I understood this correctly, if I find these on the circle, I will get the vertices of a regular foregone, which in this case, regular foregone means a square, yes? But it was not easy to guess even the first one. Here I could guess the first one, so I divide the whole circle to 3 parts and I start rotating it every time by an angle 120. But it was not easy at all to guess the first one either here. But at least you understand what is the geometrical idea behind that. So it means that if you draw a circle whose radius is this absolute value, this strange number here, which is of course a small number, yes, the eighth root of 2. Okay, so yeah, it's not that small, by the way. So, but anyway, what I do, if I want to understand it geometrically, so this means that I have a circle, yes, centered at the origin. The radius is how much? The radius is equal to that number. Yeah, so the radius is the absolute value. And then if I want all these complex numbers lie on the same circle. And of course, you can immediately see what's happening, because I don't know, this is a little bit strange number, but this one to the next one, the difference should be pi over 2. Why? Because the whole circle is 360 degrees. When I divide it by 4, it becomes 90 degrees. So it means that these numbers should be rotated 90 degrees, 90 degrees. Okay? And I hope that I have done everything right. If I have done everything right, this angle is pi over 16. I don't know how much is that. Pi is more or less 180 divided by 16 is a little bit then more than 10, yes, or something like that. So this is the first one is actually very close to the x-axis. So this angle, whatever it is pi over 16. So this is one of the roots. But if you know the other, you don't need to find the other roots by finding them. So you just rotate them. How many times? How much? 90 degrees. So I rotate this one 90 degrees. I will get this one. Then I rotate this 90 degrees. I will get that one. Then I would rotate this 90 degrees. I will get this one. Okay? And it means that, of course, if you do this precisely, and if you just do this, then what you get is a square. Okay? But of course, I couldn't do this properly. Okay. Any questions? No? Okay, so tomorrow I will complete this. So this is finished, the lesson. But if you remember, I skipped one part when I was teaching the integrals, and that is the application of integrals for probability. Okay, that is also one part of the national exam. So for the national exam, I have to teach that one as well. So I will come back and teach that one, and then everything is more or less finished. Next week, probably we will just practice a little bit on the past papers. There are not many of them we are allowed to use. So let me stop this recording now. Any questions for this lesson? Okay.